Good afternoon.
Hello.
Anyway, hi. So my name is Mark Polliger. I'm Engineering Director for Client Applications. And I'm here today with Sean Parent from Adobe Systems. Sean and I have known each other since 93, 94, something like that. Long time. When we worked together at Adobe on the Photoshop team. And Sean has done a tremendous amount, primarily in and around Photoshop up until recent times for the work that he's going to be talking about today. Put, amongst other things, automation and UI layout and just a tremendous amount of capability into Photoshop. And I guess the last couple of years has moved on into more of the research side of Adobe and has concentrated on areas primarily centering around STL and Adobe additions to them, and also sort of looking at the whole problem of user interfaces and their complexity and behavior, and why a lot of the software that we have works maybe despite itself and despite the way that it's built. So with that, I'll turn it over to Sean.
Okay. So is my mic on? Yeah. So that was a nice introduction. Thanks, Mark. I've been at Adobe now for something like 13 years. And about the last 4 years working in either our Advanced Technology Group, or now I run our Software Technology Lab, which is a small team trying to rethink how Adobe goes about building software. Now, this talk came about because Bjarne Stroustrup, who created C++, invited me to give a talk down at Texas A&M and said, "You're in the industry, why don't you come give a talk to the students about the future of software development?" And I said, "I don't know about the future of software development. I know about what I'm building, which is hopefully the future of software development. So I'll give a talk on a possible future of software development." For those of you who don't know much about Adobe, a little background information. We're a big and growing company, about $2.5 billion of revenue, not growing nearly as fast as Google or as big as Google. But we've got about 6,000 employees worldwide, very distributed. We do a number of products. Some of these you've probably heard of. So internally, we're structured loosely like this. It varies from business unit to business unit, but we have product lines. So Photoshop is not just a product, it's a product line. There's Photoshop Elements, Photoshop Extended Edition. And we have product teams where we typically have 20 developers working on a product team, about 30 testers, which surprises most people, more QE than engineering. Typically 1 or 2 UI designers working with the team. And then we have about 20 shared technology groups, which all have similar structure to the product teams, dealing with libraries for vector graphics, typography, color, help, localization, things like that. So development process, we strive towards an incremental development process, but the business we're in tends to push things into more of a waterfall process. There's a huge lag between the time, say, you have to reserve press to print the manuals, and the manuals have to be done between when you can actually ship the product. Since we do physical boxes, getting everything done in the quantities we demand takes a manufacturing ramp. And that tends to push the development cycles into more of a waterfall model where you sacrifice quality early to get the features in so you can write the manual and ship later. We ship mostly Macintosh and Windows simultaneously. English, French, German, Japanese are our tier 1 languages, and by the time we're done, usually about 3 months after the first ship, we've covered about 24 languages with the products. So if you're going to talk about the future of software development, I thought I'd do a little research on what do the analysts say. You've got lots of buzzwords. I spent some time going through analyst reports. You hear lots about Java and C# and XML and web services and open source. And some of these things I agree are important, and some I don't think are very important. Best practices and methodologies is listed first up there because that's where most people think the problems are. I pulled some quotes from analysts that I just thought were interesting. The second one being the most interesting. Microsoft rolling out a new development process. This is Directions on Microsoft, which is an analyst publication that's usually very friendly to Microsoft. And the fact that they would go through the trouble of putting together a whole development process when analysts say they don't think it will necessarily help the company ship its products on time or with fewer bugs. The top one is talking about the problem of security and the number of analysts who believe that the solution to security is more and more testing, which I think has very, very diminishing returns. If you already have 30 QE people to 20 engineers, if you double that to 60 QE people testing for security holes, you might find another quarter or half of the security holes out there. So you're not going to close the holes that way. Ultimately, though, this is why I think the status quo in software development fails. This is a quote from John Bentley from his book Programming Pearls, published in '86. John went around teaching classes on how to develop software and gave a test to mostly senior engineers at IBM and Bell Labs and asked them to write the binary search problem. Given a specification, write a correct binary search. 90% of the programmers failed finding bugs in their solutions. And of the solutions where they couldn't find bugs, many of them they still weren't convinced that they were correct. Okay. To put it in perspective, this is a correct solution to John Bentley's binary search problem. Okay. And they were not given just like a few minutes to do this. They were given several hours to try to do this. Photoshop uses the same problem and has for many, many years as a take-home test. And more than 90% of the candidates just fail miserably at coming up with anything remotely resembling this piece of code. I think the worst case is probably 48 pages or something like that of code. And once you figured out what the 48 pages of code did, it was wrong. So that's a problem. Now, John Bentley's own solution is considerably more complicated than this solution, okay, and considerably less efficient. So our experience at Adobe in teaching programmers is that the same rule holds, and you can take, PhDs from Stanford, which comprises a large section of Adobe's advanced technology group. And 90% of the PhDs from Stanford can't write a correct binary search. So how in the world do we ever ship a product? Okay? If you can't write that much code correctly, how do you get Photoshop out the door? How do you get Word out the door? How do you get Google Desktop out the door? Well, these are actual bug graphs from product cycles inside of Adobe. And this is a clue. What's going on here is we're not solving problems. We're approximating solutions. And some of these curves, this one in particular, I don't believe. What happened here is there was a projected ship date out here. The little peak here is because QE stayed over a weekend to finish their regression tests while engineers went home. So you had a little peak, which caused a panic, which led to a nearly linear slope. The linear slope is not fixing bugs, it's deferring bugs. Okay? So we never hit a 0 bug count, even pretended to here. You'll see we're still off 0. But in reality, what's not shown here is the number of bugs that were just plain deferred off the bottom. So that's what our current programming methodologies do. They allow us to iterate and refine and approximate a solution, but never actually come up with a correct solution. So one thing my team's working on is studying how do we go about writing correct software. Okay? If you want to write it correct to begin with, how would you go and do that? And this leads us to generic programming, where my team spends a lot of our time. The idea with generic programming is you start with a concrete algorithm. Okay? You refine the algorithm, reducing it to its minimal requirements. clusters of related requirements are known as concepts. And we have a little more formal definition that we'll get to in a minute. Then you define the algorithm in terms of the concept supporting maximum reuse. So if you have an algorithm and you can then prove that it's a correct algorithm, now what you want to do is lift out that algorithm so it's written in terms of its minimal requirements so that you can reuse it in the most number of areas. Now there's a parallel here between mathematics and generic programming. Programming is mathematics. Okay? In generic programming, we have what we call semantic requirements. In mathematics, they're called axioms. Okay? What we call a concept in generic programming is an algebraic structure, like a ring or a monoid in mathematics. Models, we use the same terminology. In computer science and in generic programming, what we call an algorithm is just a theorem. Okay? So an algorithm is written in terms of concepts, just as a theorem is written in terms of an algebraic structure. Both rely on axioms for the correct definition. So a regular function, a function with no side effects, corresponds to just a mathematical function. And the one thing we have as computer scientists that mathematicians don't have to worry about is complexity. Right? We have to worry about how long does it actually take to compute the answer here. Now, we can refine a concept just as mathematicians can refine an algebraic structure. So a mathematician would say that a monoid is a semigroup with an identity element, if you ever took any abstract algebra. Okay? That's an equivalent statement to saying, roughly equivalent, a bidirectional iterator is a forward iterator with constant complexity decrement. Okay? So you can take a concept and add additional axioms, semantic requirements, okay, in order to refine it. And that will give you something which is, in some sense, more powerful in that you should have algorithms that you can execute more quickly on it, more algorithms, but you'll have less models, okay, less types that you can actually use with this thing. We also refine algorithms, which is something mathematicians tend not to do. Mathematicians typically do not refine a theorem. A refined algorithm is saying if you have a concept which is itself refined, then you can perform the same operation that you could on the unrefined concept on the refined concept, but potentially you can do it with better complexity or reduced space requirements. Okay. So in C++, this is the way concepts appear in the existing C++ standard. They are tables that appear in the standard itself. They're not expressed in code. And in fact, the tables are very, very weak on their semantic requirements on this end. So my group takes it a bit more seriously and applies much stronger semantic requirements to what each of the axioms are. So where here, if I back up, we define the notion of copy to say that T is equivalent to U. The reason why the standard uses equivalence instead of equals is because it doesn't require that equal be defined in order to define a copy. Okay. But if you want to define what it means to have a copy, then you have to require equality. Now, concepts enable equational reasoning about your code just as axioms and algebraic structures enable equational reasoning about mathematics. Through concepts, you can prove algorithm correctness, okay? And you can then reason about your system in its entirety. Generic programming often gets confused with, angle bracket templates in C++. Generic programming is not a programming style as object-oriented programming is a programming style. Generic programming is a way to reason about code. I can reason about code through the axioms defined through generic programming, even if the program is written in an object-oriented style. Okay? The same axioms hold. So the axioms have to exist and the theorems have to be correct if the system functions correctly and works. And where it doesn't, it's because something's been violated. Okay? So you can use the same ideas from generic programming to analyze an existing piece of code as well as write a correct piece of code. Now, in C++, it's pretty horrible right now. So we can't do generic programming in the language. So what we do is we approximate it with templates, which are really just macros, and we have comments. So when I say type name I, or in STL it might say type name input iterator, or random access iterator, and here I say I models random access iterator, just to be a little more explicit. Random access iterator is naming a concept that you can formally define. Regular is naming a concept that you can formally define. In fact, that was the definition of regular a couple slides back. Okay? So in C++ 0x, if anybody's been following the progression of the language, much of what's written up here in comments you can now write in code in your C++. So this is a big part of what my team is working on. Now, this brings us to a small pause in the talk. Okay, so great. So we can write sort, we can prove sort's correct, and we can write reverse, and maybe we can write some nice image processing algorithms going this way. So how do you get from there? How do you get from forward iterator to Photoshop? It just seems like this very large chasm. Okay, how do you get from STL to Microsoft Word? How do you span that gap? So we're going to change gears a little bit here. I have a conjecture, which is that all systems eventually grow and turn into some kind of network problem. Okay? So if you have any problem of scale, okay, what that usually means by a problem of scale is that you have to be able to reason about the system as a whole by being able to reason about it locally. Okay? Such systems become graphs with sets of rules that apply to the graphs. And those describe an awful lot of the systems that we build. So if you go and you look at Photoshop, what you'll find internally is it's become this massive network of objects. These objects are all interconnected. They form some giant implicit data structure. There is messaging between the objects. So those messages do something, hopefully. That's an algorithm. Okay. We use tools like design tool or like design patterns. Scott Meyer's 50 rules for writing a C++ program to come up with local rules that if we apply them, hopefully we get a correct system out the back. And then, once we assemble all these objects, we iteratively refine and refine and refine and refine until we can ship the product, until it's good enough. So, take a moment and define a generic algorithm for solving a large system. If you're just, build Word, how are you going to go do it? Well, identify the components and how they connect. Okay. This is my generic algorithm. Organize the system into a directed acyclic graph. Okay. Everybody know what a DAG is? Hopefully, engineers here. So the reason why a DAG is important, okay, if you have, a DAG is just a directed graph with no cycles. So if you have a cycle in your system, it makes reasoning about the correctness of that system very difficult. Okay? You can no longer reason about the correctness of the system with only local knowledge. You have to have complete knowledge. okay, and know what the effect of that data feeding back on itself is. So you want to define your system in terms of a DAG. Now, of course, you're going to have loops. You're going to have things that do iterate. And what you want to do is encapsulate those, figure out where the loops in your graph are, and figure out what the algorithm is that's done by that loop, and write that algorithm, and make that algorithm be just a node in your graph. It becomes just a processing node in your graph. And then ensure that for all possible states in the system, this DAG is going to be changing, things are conditional, stuff coming on and off, that cycles don't pop up, okay? That this thing stays a DAG. And then make it generic, which means once you have this for Word, figure out how you describe similar structures to build other applications. Now, this all sounds very complicated, but the idea actually, for me, came from this. One of the things I worked on at Adobe was a layout engine, which is used in most of the Adobe products at this point to lay out user interfaces. And it's a constraint system of sorts, but it always forms DAGs. And I had this realization one day that I could solve a spreadsheet inside of the layout system, and that I could turn the layout system into a spreadsheet if I wanted to. And this is why. They both form DAGs. So this is just a graphical representation of this. We're just summing up 3 numbers. Well, I can draw it like this. Okay, I've got 3 cells feeding into a plus operator and coming out with 1 result. When you start to talk about constraint systems and declarative programming, which is what we're talking about here, people have a panic attack, mostly because in school they might have been exposed to the wonders of Prolog. Prolog is a rule-based system. In some sense, a spreadsheet is a rule-based system. But Prolog was striving to be a Turing-complete system, a complete programming language where you could write anything. You can sort in Prolog. You really don't want to sort in Prolog, okay? So sorting is an iterative loop. If you have a rule-based system that's iterating, it becomes very difficult to reason about. So what we're talking about here is more along the lines of something like HTML or a spreadsheet or SQL or Lex and Yak. Those are also declarative rule-based systems of sorts, okay, that strive not to be Turing-complete. Some of them are accidentally, but in general, you stay away from the scary edges. So part of what my team's been working on is something called the property model library, which is to apply these ideas to a real system. And this is the domain we went after. It's a piece of a user interface. So this is the data flow of a small section of an actual user interface in a product that Mark Poliger is very, very familiar with. The symbology here are basically these 4 items in the middle are widgets, UI widgets. You can think about them that way. So the top 2 editing numbers, the bottom 2 are checkboxes, just Booleans. And we have some code that sets up the dialog, so it populates these widgets with stuff. And then we have a bunch of event handlers, so if I enter a value into one thing, then it percolates and changes the values in my UI. And I literally went through the code and drew a connection, drew an arrow anytime one piece of code was connected to another piece of code. Data could flow from there to there. And the complete section of this dialog has 14 widgets, I think, in the middle. I stopped after 4 and said, screw it. It's just a big ball of spaghetti. I did add this one box down here, which is script validation. So what's happening here is, we have a UI. This is setting an image size for a particular width and height. And you can also drive it without a UI attached by executing a script. And all the validation logic that's contained in the spaghetti code of event handlers has to be replicated into the script validation code so that you make sure that whatever I record up here, I can play back without the UI and not end up with an error. So in fact, if you look at Adobe's code base, a third of the code in our products ends up being event handling code of this sort, part of the big ball of spaghetti. And if you survey our bug database, you'll find that half the bugs during any development cycle are in this body of code. Now, when I first saw this, I thought, cherry picking, go after this problem. I come up with a solution, and I'm the hero. I eliminate a third of the code and half the bugs. What I didn't realize was this is indicative that it's a very hard problem. So, and here's why. If writing a correct algorithm itself is difficult, then writing a correct algorithm when it's implicit, okay, when you don't actually have the algorithm as a loop in your on one page, what you've got is a message to another object that eventually loops back to you or not, and the algorithm is buried in there, gets to be almost impossible. So, start to break down this problem. How would we define it? Well, you have to start and say, what is this thing? What's this event handling logic? How can we even define this? And we backed all the way up and said, we don't even have a good definition of what it means to have a user interface. So we came up with these as working definitions for what it means to have a user interface. And it's just a system that's designed to assist a user in selecting a function and providing a valid set of parameters to that function. So what distinguishes a UI in a product from, say, consuming a movie is the fact that the user is trying to do something. He's selecting a function and then executing it. Now, a graphical user interface is just a user interface that's visual and interactive. A big part of the code we're talking about here is not the code that deals with selecting the function, right? You pick the menu item, you've got the dialog box, or you're on the palette, and the function is implied. It's going to set a set of properties on your document. But what does it mean to assist the user in providing a valid set of arguments to that function? So we have two loaded terms there. One is valid. We know what arguments to a function are. What does it mean that they're valid? And what does it mean to assist? So valid is pretty easy. It's just a predicate that corresponds to the preconditions of the function. Assist, there are many, probably an infinite number of ways that you can assist a user. But if you go and look at the applications, we have general patterns, and you can start to categorize these patterns. So here are 4 that we're dealing explicitly with. One is validation, which is given that you have said predicate to know whether or not your preconditions are satisfied. You can simply, validation is simply rejecting bad input, saying, no, you can't do that. Okay? Correction is the idea that, let's say I have a valid set of input, and now I poke a value, and now the system's invalid. How do I get it back to a valid state? That's correction. So prediction is letting the user specify the values for the function in terms of the desired result. Okay? So if I want to take a file and split it into 4K chunks, then depending on the size of the file, I'll get some number of files out the back. So the user could specify the file that they want and how many pieces they want out the back, and you can calculate how big the chunk needs to be. So prediction is specifying the parameters for the function in terms of the desired result. Then related values. So if a user is specifying, I'll use our example here, the size of a document in pixels, which might be the only thing the application cares about, that might not be a natural user interface. There's a related value there of inches, which is related to pixels through resolution. So you end up with related pixels or related values through which you can define the arguments for the function. So let's make this a little more concrete. Flip to a demo here. Are there questions at this point? People following? Think I'm nuts? Okay, let me hide that. Okay, so this is a little picture of the UI that we had the big ball of spaghetti about before. And this is fully functioning here. Okay, so we can change values. There are constraining proportions to the original document width and height, which is up there. We can toggle our display between percent and pixels. We can unconstrain and change a value. And then we can reconstrain, and the other one updates appropriately. And if you put this in percent, they'll always be equal. So that's the basic idea for this UI. Over there on the left, you see the complete description for the underlying model for that. And we also have a description through our layout language of what the visual portion of the UI looks like. So this is looks very much like a box model. The solver is a little more general. It automatically does things like line up colons and has a little more smarts underneath it. But things are described in terms of a basic box model. And you'll see these bind statements against things. There's bind here, bind here, bind here. The bind statements are what connect the UI to the model. So the way most people tend to write an application is the application logic reaches up into the UI and mucks with it. And if your application is doing that, your application knows all about the UI. You can't have an alternate UI on it. You can't reshare that logic for scripting. So here what we've done is we've factored out the description of the model, which is how these properties are connected together independently from what UI is bound to it. And we can demo that by opening up another UI. So this is another UI that we just attached to the same model. We can see the original document width and height down there. And you'll see these are actually attached to the same instance. So if I change the UI, or if I change the values up above, they're reflected down below. And it's running non-modal, so I can change it here, and it will change up above, and unconstrain, and change and reconstrain. Okay, so two alternate UIs. Or I can do a third UI. And here, I wanted to represent my percentages as sliders. So I've got two sliders, and it will roll through the numbers and all the other views. And it's pretty traditional model view controller stuff that you probably could have seen demoed on Smalltalk systems at Xerox many years ago. But somehow we've forgotten how to do this. What we've forgotten how to do is define models. Okay? So that's a basic idea of what we're talking about here. Let's flip back. Now, when I came up with that piece of code, I went and found one of the best engineers at Adobe, a guy named Mark Hamburg. He was chief architect on Photoshop for many years. He's responsible for Photoshop Lightroom, which is recently shipping. And I said, hey, Mark, this little mini image size is just a portion of the Photoshop image size. It's just got a couple of connections. Fully specified. I'll tell you exactly what the specification for this dialog is. Write the code in the language of your choice, in the framework of your choice. I don't care about how your UI is laid out. I just want the logic for this dialog. This, you can zoom in on it if you want or get really close to the screen, is his resulting code. It's written in Objective-C to Cocoa on the Mac only. The gray areas here roughly correspond to the logic that's in the model. And the rest of the code is code that, given a change in the model, reaches up into the UI and manipulates it. It's all the event handlers going on there.
This isn't the full program, right? The full program would also include a nib file.
Yeah, there's no nib file here. There's no description of the UI. This is just the logic for it.
So Sean, you're not using any bindings then?
What's that?
Since there's no nib, you're not using Apple's bindings.
Oh, no, it is. There is a nib file, and there are bindings.
You're just
So
not showing it.
it's just not showing it. Okay.
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 Using bindings.
Yeah. 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 This is not like trying to recreate the world. This is as small and tight as he could get it. Okay. This is my solution in comparison.
Well, now, excuse me.
Okay. Yeah.
A huge chunk of code that's required to interpret them.
There's,
Your solution.
yeah, so the amount of code to interpret that is 2,000 lines. Hopefully the next time I get around to rewriting it will be about 1,500 lines. In comparison, the code for the complete version of image size in Photoshop is 6,000 lines. So my complete system for the UI layout engine, the solver for the models, and both the parsers is smaller than 6,000 lines. Okay. So this is the resulting structure that, if I were to draw that, this is what we end up drawing. Okay. So here, the notation here is a solid arrow with a solid point is a fixed connection. Okay, that's a directed connection. The soft arrows here can go either way. They can flow around. The dotted line here, this is a conditional connection. So there's a predicate attached to that, which can toggle it on or off. Okay. And that describes the complete system. So a little more about the structure. It's always expressed as a bipartite graph. It's very similar to spreadsheets, except directionality can be determined at runtime. So you can kind of flip things the way they're going. Data is flowed from higher priority cells out towards dependent lower priority cells. So there's a link reversal algorithm that's employed to reserve soft cycles, which there are systems where if I tried to pin 2 values, it becomes overconstrained, but if I only pin 1, then it's not overconstrained. So that's a soft cycle. Hard cycles are very easy to detect, so we just detect and reject them. In soft cycles, we just solve them. Now, kind of a full notation here. We have sources, which just have n outputs. Sinks just have a single input. A cell can have 0 or 1 inputs, meaning it can be derived or itself can be a source, and the remaining are outputs on it. And then relationships have n inputs and 1 output always, and conditional relationship is the same with just a predicate on it. So those are the basic computational structures for this system. Now, we're attacking 30% of the problem. We're getting pretty good traction right now. Last time I looked, we had, this is going in as part of future Photoshop and several other apps. And last time I looked, we've got 20, maybe 25 dialogues re-expressed this way, and all the thousands of lines of code underneath them ripped out. So it's took a long time to get traction, but now that I have traction, the roll is actually going pretty quickly. My estimate is that 85% of the existing code base can be replaced with small declarative descriptions and a small library of generic algorithms if you go and look at a product. Now, that's not these small declarative descriptions. There are other problems that manifest themselves in the applications, and they need to be solved. But that's my gut feeling looking at the application code. In fact, if you look at all of it, I think we're about 2 orders of magnitude off from the minimal expression for any large application, which Photoshop is roughly 3 million lines of code last time I counted. which means I think you ought to be able to express all of Photoshop in about 300,000 lines of code. Am I off there? Sorry, 30,000 lines of code. I'll let you guys read the rest. It pretty much fills it in. So if you guys want more information, I've got some links up here. We've got our open source site, all the example here, the example application that I'm running this through, and I can give examples all day of the system, is available on opensource.adobe.com. You can download it. All the code is there. StepanoffPapers.com. Alex Stepanoff, if people know who he is, the guy who created STL. He works for me on my team. And we have a website just for his collected works. One of the things we're working on is a book, kind of bottom to top here. These are the drafts of the book. The first failed draft, second failed draft, and the draft we're on. So we will get this thing out one of these days. But please read them, give us feedback. We're specifically most interested in feedback on the top, which is our current attempt. This is the book that I think Alex should have written when he released STL, well, almost 15 years ago now. People look at STL and think it's a nice container and algorithm library, and not it's a different way to think about code. So the point of this book is to explain what it means to do generic programming, not to teach you about how to use STL. And that's it, Adobe's tagline. Question?
One concept that appears a lot in programming that you didn't seem to address much here, and also in mathematics, is concurrency. Have you done any work in managing concurrency problems?
So,
Repeat the question or use the microphone?
sure, I can repeat the question. Yeah, so the problem of concurrency, we've done a little work on concurrency, usually when we're stuck on something else. Our two side projects have been threading issues and Unicode issues. I think the same basic techniques apply to concurrency, meaning that successful systems that I've seen that are concurrent are written basically in one of two ways, either in a structure similar to a Unix pipe system, which is basically flowing data out into a DAG, and at each node you have a queue, and the queue provides enough elasticity at the join so that you can wait until you have enough data to progress along the DAG. The other systems are ones where they are algorithmically parallel, where I can do a reduction algorithm, things of that nature. So if you look on kind of the algorithm parallelization side, there's a lot of work that's been done on, there's the Stable project at Texas A&M, which is parallelizing STL algorithms. I'm drawing blanks on example, but there's many out there, especially in the domains of linear algebra, image processing. And we have a fair amount of work going on at Adobe in those domains. On the how do you structure an application into a sequence of processes, basically, even though maybe they're threaded, they're not full processes. But how do you go about building an application like that and describing the structure much as you would, say, on the command line of a Unix shell to string together a bunch of Unix tools? How would you build complete applications, piping a bunch of components together? And that's where my team's most interested, and I think there's some good work to be done there. So I don't know if we'll ever get to it seriously, but but that's my thoughts on it currently. Yep.
I see you're trying to promote STL as a generic programming language rather than the other stuff you described as, but then you didn't actually use any C++ or template metaprogramming in your solution. I'm just wondering if there's a reason for that.
Yeah, the code under the hood certainly uses templates and generic programming. The language itself is...
Scripting language in terms of like a template or something, so that C++
Oh, do it as like a metaprogramming language? it's not part of our goals. One of the guys at Adobe has done that for the layout engine. There's a domain-specific language done as metaprogramming in C++. Our goal is to get the mathematics correct to describe what the computational structure of these systems are, and give a generic description of what it means to solve one of these systems, not to do C++ metaprogramming.
The follow-up question, I guess, is if you are you trying to convince people that C++ is a good generic programming language if you're not even using a generic programming language?
Well, all the libraries are implemented in C++. Do I think C++ is a good generic programming language? I think C++ is the closest approximation that we have to a good generic programming language, and getting better. You know, Alex wrote STL in Ada long before he wrote it in C++, and it's been written in portions of it in Scheme and Java and C, and we still tend to prototype code sometimes in Scheme. So it's the ideas of generic programming supersede what language you express them in. You know, typically what we do is we work out what's the generic description of this, what are the axioms, and what is the algorithms, and then you go through the painful process of how do you map that into C++. You know, what I want is to just be able to write a type function, and what I have to do is write traits classes and partial specializations to get them to dispatch in C++, because I can't just write a function in a natural terminology that manipulates types. And you had one more point there, which is, are we trying to convince people of this? I've got nothing to sell. I mean, we're a very small team. Everything we do is open source. The reason why we open sourced it is because it's interesting problems, and I'm interested in collaborating with other people. We do a lot of work with Indiana University and Texas A&M. I see a general trend in this direction. I think eventually this approach wins out. You know, by this approach, I just mean a mathematical approach to programming. I don't think we can continue to treat programming as an approximation. Our systems are just getting too big and too complex. And without perfect approximations, it just means more and more and more failures. So.
What kind of bug rates are you seeing with this approach, and are the bugs easier to solve, or are they harder?
So we're seeing pretty much 0 bugs so far, once you have your description out there. The challenge is getting the model written in the first place. And the system right now does a fair amount of checking, not quite as much as I would like, but it does enough that it tends to bitch at you. So the whole reason for coming up with a way to draw the picture, and eventually we're going to wire that in with GraphViz and use dots so the system can automatically draw the pictures for you, is that you know, if the system bitches and says there's a cycle here because you overconstrain the system defining too many relationships, you need some way to figure out, well, what did I do wrong and how do I get it right? So there tends to be a more thought process up front, and it's more difficult to get kind of anything working. Once you get it working, you're done.
So back to the question of whether C++ is a good language for generic programming.
Yeah?
You talked about the inadequacies in C++'s support for concepts, and especially about the goal of expressing concepts at runtime, not just at compile time. What is missing from Haskell type classes that would make them useful as a representation of concepts?
I would go and read, let's see, it was Doug and Jaco and that crew did a survey paper not too long ago that covers that in far more depth than I could give it justice here, because I'm not much of a Haskell programmer. My opinion is I would program in Haskell if I had a reason, or some, whatever language worked the best, if I had a path to deploy that in products. To fund my team, I have to ship software. And right now, that means I ship in C++. So I'm not a religious zealot when it comes to C++. I do think it's the best language out there for concept-based programming, but.
So when you're making UIs, like as a programmer, you sort of already naturally think of it as sort of a signal network when you're designing it. You know, like this component connects to that component, I'll register a callback, blah blah blah. So it sort of
Right.
lends itself to your network model language for describing it. But have you tried applying it to like other parts of the system that aren't already UI?
We've done some somewhat wacky things with it. We've used the modeling system to describe overload sets for functions in C++. So you describe the relations on a set of parameters, and the system will go through and iterate what all the possible overloads for that function are that have any meaning. We've used it to, the layout engine, which I didn't talk too much about here. We've used the layout engine, which usually does 2D UI layouts, to describe 3D worlds, and the same thing that connects baselines made sure that that you had paths between rooms, that you didn't end up with completely walled in spaces. The solver here has been used for doing dependency tracking for installers. What else? Somebody at Apple used it for doing music mixing. And the graph solver itself is fairly independent of what the equation is on the node. It doesn't care what the function is on the little circles, just that things are connected. So you can plug whatever you want in there. So people have used it for music processing. How far it goes, I don't know. I mean, we're from the UI standpoint, we solve a good chunk of the problem right now, but we still have little pieces that are hanging out that we're focused on, not figuring out more domains for it.
Does this approach lend itself to maintainability? I mean, you said the big problem is coming up with a model.
Yeah.
Now, if the real world wants something else or changes a little bit, do you already think about that?
Yeah, it lends itself pretty well. The interesting thing is developers have a hard time changing the way they think. Okay, so what tends to happen is frequently the request comes in and says, well, the UI designer says they want it to work this way. And that might just be a view behavior on the outside. It has nothing to do with the model. The model itself doesn't change. And getting developers in the mindset where if it does come and impact the model, I mean, this is a model of parameters to some function. And the goal is to try to make the model as complete as possible, and that gives the UI designer as much flexibility as they want to put a big UI on it or a little UI on it. You don't have to expose everything. You can expose whatever subset you want, so long as the model is consistent and correct. So the system tends to be fairly easy to maintain. What tends to be hard is recasting the problem into what is the relationship here that is being asked for? How do I express that? And since what I'm modeling is typically a set of parameters to a function or a set of properties in a document, going from that relationship to say, well, what does that imply about what the function has to do? These things don't just exist externally. Okay, so you have to, I'm going to go change the behavior of this function and what it does, and then I'm going to go and express that in my model. And it's just a different way to think about software. I mean, my experience so far has been the more years somebody has spent doing object-oriented programming, myself included, over a decade's worth of object-oriented programming, the more trouble they have expressing things in terms of the relationships within the model as opposed to how events are flowing through the system. So one typical example, people will say, well, I want this checkbox. When this checkbox is checked, I want this thing to be disabled. Okay. Well, what it means when something is disabled in the system is that it's disconnected from the output. So that no matter what value you put into that cell in the model, it could have no effect on the result. Okay. So there isn't any way to say, disable this thing when I click this checkbox. What's implied by that request is that there's some relationship to that checkbox that tends to disconnect that cell from the output. What is that relationship? Write that down and the UI will just work. Okay. So, other questions? I've got, I don't know, 3 minutes. I can give more demos or answer a question or.
Have you had any interest in your QA team using these models as sort of a spec that they can work on?
Yeah, the QA team likes the models because it gives them, a very concise spec of what's going on. The other thing is we have a set of just command line tools, so you can check the models independent of the app. And it's also nice, you can, we've got a little sample app here, so you can bring up a model, with no function attached on the back end. So I can bring up like the complete image size from Photoshop with all the 14 widgets and all the connections between them, and fully test the thing without launching Photoshop. Okay? And from a UI designer standpoint, it means that I can play with my UI and say, oh, I want 3 panels instead of 2 panels, and I want a revealy widget, and I want a slider here, and never have to touch the code. So they like that. The one thing where we do have tension with QE is used to working in kind of a puppet string world, where a lot of the automation test tools will like reach into the UI and say, what's the state of this checkbox? And in our system, our checkbox don't have any real intrinsic state. They're simply a view of the underlying model. So you can ask the model, what's the state of this cell? But it doesn't make any sense to ask the checkbox what its state is. And our automation QE team has a hard time getting past that hurdle. They're like, well, what if the model is correct, but the connection to the UI is wrong? How do we test that? So I think that's just friction that will fold out over time.
90% of the computer scientists that we teach came from binary search. How do they fit into this new model of programming? Do you think this is easier to teach them, or do you think it's not as important to teach so many as long as a cluster of people can use this?
Yeah, so I think eventually you end up with a shift in what it means, for people to be programmers. I think assembling collections of, say, generic algorithms is an easier task than writing the generic algorithms to begin with. I think even constructing these models for a system is somewhat easier. I can show you it's 100 lines for the image size in Photoshop, and it's way easier to write that 100 lines than it is to write the 6,000 lines of code in Photoshop. And Mark can probably attest to it, and the 6,000 lines is also wrong, and I can prove to you it's wrong.
I didn't write that code.
Okay, I wrote one version of it. So I do think it makes it easier, but I think what you want is a shift. I mean, at this year, at this point in history, I think it would be great, if you could get a PhD by trimming a couple of cycles out of one of the STL algorithms. That should be, get you a PhD. Coming up with a new algorithm that's generally useful certainly should be worth a PhD. And yet, right now, very few people, we don't have a massive library of this stuff. We have very small libraries, and everything's very primitive. And my team spent the last week and a half working on a formal definition of integers, because the mathematic definition of integers doesn't hold up real well when you have integers of a fixed range, right? We can define z, but we can't define what z over a range of 0 to n is. because n is z if you. What's that?
ZN?
Z sub n, which doesn't quite capture, say, signed arithmetic. It works pretty good for 2's complement unsigned. So also piano axioms, which is how mathematics are defined, are in terms of successor. So you start with 0 or 1, and then you add 1, and you can build up all of mathematics with just successor, with basic increment. From a computability standpoint, that's very unsatisfactory. Right? We don't add 2 numbers by 1, 2, 3, 4. Okay, it just doesn't work that way. So coming up with kind of recasting mathematics into axioms that apply to computer science is a part of the work. And eventually these should be textbooks. And we need our Eulers and our Euclids and those folks. Any more questions?
So yeah, this is back on. So thank you, Sean.